Welcome to lesson 12, implicit differentiation. So in all of the previous lessons, the equations that we were working with were defined explicitly. And what that means is the y equals, and everything on the other side is in terms of x. So there's some examples right here of explicit equations. It's the kinds of equations you're used to, polynomials, trig functions, etc. But you'll notice that y, which is the dependent variable, is written on one side, and the other side has all of the x's, no y's, and there's no x's on the same side as y. Okay. However, there are other kinds of equations, and you've probably seen some of these before, where the x's and the y's are not isolated from each other. So these are called implicit equations. Okay. So what we're going to be doing in this lesson is finding out how to take a derivative of an implicit equation, because everything we've done so far has been these explicit derivatives, and we take the derivatives, we're finding dy dx, or the rate of change of y with respect to x. So as x changes, how does that make y change? So in implicit equations, we still want to find the same thing. We still want to find the rate of change of y with respect to x. And so what that means when we go through one of these and take a derivative, we're going to take derivatives of y's. And that would be dy dy, the derivative of y with respect to y. So we use the chain rule to multiply that by the derivative of y with respect to x. Okay. So I'm going to show you in this first, these are very, very basic terms that we're going to take the derivative of. You are used to, if I am going to take the derivative with respect to x of an x, then we just use our usual rules. Now, if I'm going to take the derivative with respect to x of a y, okay, I'm kind of like thinking of it as, it's kind of like thinking of it as a chain rule. So my inside is the y, and my outside is what I'm doing to the y, which is cubing it. So when I take the derivative, oops, so I was going to just write equals, I guess, of the outside, I'd have 3y squared, so 3 inside squared, and then I'm going to multiply by the derivative of the inside. But you're like, the derivative of y, but with respect to x, which is a dy dx. So what I've essentially done is taken the derivative of the y term using your usual rules. But then because it's a derivative of y and I want it to be in terms of derivative with respect to x, I have to then multiply by dy dx, the derivative of y with respect to x, to effectively use the chain rule. So let's look at a couple more examples. If I'm going to take the derivative with respect to x of x squared, that's 2x and nothing changes. I don't need a dy dx because I'm already taking the derivative of x with respect to x. But when I go to apply that to 2y, I'll take the derivative with respect to y, which would just be 2, and then multiply by dy dx, my chain rule, to make it a derivative with respect to x. One more try here on number 4. I have a product of two things, so I need the first one times the derivative of the second one. Well, the derivative of y is just 1, but then I multiply it by dy dx because it is a y term. And then I'll do y times the derivative of the x, which is just 1. So I'm going to kind of ask you to recap what's happening here. When we take a derivative with respect to x of an x expression, right, we just use the rules as usual. It's what we're used to doing. But when I take the derivative with respect to x of a y expression, what am I doing? So I'm first going to take the derivative. I'm going to write deriv there in terms of y as usual. So it seems like I'm using the usual rules, just applying them to a y. But then I multiply by dy dx to apply the chain rule. If you have a better way to explain that to yourself, you notice I said recap the process in your own words, then you certainly should fill that in a way that makes sense to you. So we're going to do some guidelines here. What we just did was basically the first step. It's like the bare bones of just taking the derivative of a y with respect to x. But how do we actually take the derivative of an entire implicit equation? So we're going to start by doing what we just did. We're going to differentiate. And we've got to make sure we differentiate both sides of that equation. With respect to x. Oh, it looks like talks to x. And what that means effectively is you're going to multiply any derivatives that you take of y terms by dy dx. Only when you take the derivative of the y do you need to multiply by dy dx, because it is part of the derivative, the chain rule. Then you got to solve for dy dx. So what we're going to do is we're going to collect all terms with that dy dx on one side. And we'll move everything else to the other side. Factor out the dy dx. And then you'll divide both sides to isolate dy dx, get it all by itself. Okay. So then you will have solved for dy dx. Okay. So let's practice doing that. We have an equation here that's got x's and y's, and so we're going to apply implicit differentiation to find dy dx. So I'm going to go through and take the derivative term by term. Every time I have a y term and I take its derivative, I need to multiply by dy dx. But every time I take a derivative of an x term, I do not. Don't forget to take the derivative of the other side, particularly when it's a constant. I often see a lot of people leave it as like a 9 in this case. Okay, so the next step, once we've done the derivative, is to get the dy dx by itself. So these two terms have a dy dx. I'm going to leave them on this side. And I'm going to move the 2x and the 2 to the other side. So I would have been adding a 2x to both sides and subtracting a 2. Now factor out your dy dx. You could have done that in this last step at the same time. That's fine. I just kind of wanted to show in the first problem each step individually. And then you're going to divide both sides by this thing that's multiplied by dy dx to get it all by itself. So we'll have 2x minus 2 over 4y cubed minus 6y. And I noticed that everything has a factor of 2. Of course, I've run out of room. So come on, come up here. I'll factor that 2 out of the top and a 2 out of the bottom and cancel those. So my final answer will be x minus 1 over 2y cubed minus 3y. To answer the question, do I have to simplify? Yes, always. It's never really a question you need to ask because the answer is always yes. Okay. I did want to make one comment. I do see people who often ask me, can I write this dy dx as y prime? So in other words, that first line there would have been 4y cubed y prime minus 6y y prime plus 2 minus 2x equals 0. And you look at that and you go, oh yeah, that's shorter, right? It's fine to do it that way. But I guarantee you that sometimes these get lost. They look like y's, or you think it's a y to the first, your prime doesn't show up very well, and so then you think it's a y. So I never write them that way because I don't want to lose them. So I take the extra half of a second of my life to just write dy dx. So it's your call, but just want to answer that question since it comes up a lot. So the next one asks us to find the equation of the tangent line to the graph. So it gives us the equation, and then it gives us the point of tangency. So equation of the tangent line means we need the point, which is right there, and the slope, which is where the derivative is going to come in. So we're going to need to take this derivative first and then plug in the x and y so that we can find the actual slope. So, whoops. Let me start off with x squared y. Well, that's a product. So I'm going to need a product rule. So I'll do x squared times the derivative of y, which is 1 dy dx, plus y times the derivative of x squared, which is 2x. So that those two terms are the derivative of x squared y. And then now I'll do the derivative of y squared x, which is also a product. So y squared times 1 plus x times the derivative of y squared, which is 2y dy dx. And that all equals 0 because the derivative of -2 is 0. Okay, so we've reached that stage where we want to now try to collect all my dy dx's on one side. I have 1, 2. So here's what I meant when I said you could do this at the same time. I'm just going to pull the dy dx out and look at what's left. So I have an x squared and a 2xy. So you see how I kind of did that all in one step. It's not too tough to just pull the dy dx out at the same time. And then I need to move these two terms to the other side. So they're both going to be negative. And so I have dy dx being negative y squared minus 2xy over x squared plus 2xy. Now I'm not done because remember I'm trying to find the equation of the tangent line. So I have my point. I'm going to plug in the -1 and the -1. Well, that's a lot of negatives. You got to be sure to keep them all straight. Okay, so let's talk through this here. -1 squared is -1 squared is 1, but then it's times a negative. So that's -1. Remember the exponent comes before the multiplication. Exponent first, then multiply. And everything else here is being multiplied. So I have a -2 times a -1 times a -1. So that comes out to a -2. And on the bottom, I've got -1 squared, which is 1. and 2 times -1 times -1, which is 2. So it looks like I have -3 over 3 or -1. So that's my slope. And if I'm going to write the equation of the line, it's y minus the y coordinate equals slope times x minus the x coordinate. So there is my equation of the tangent line. All right, and we got one more example here, trying to find y prime, which is the same as dy dx. And again, you'll see I've got x's and y's all mixed together. So I'm going to need to use this implicit differentiation. Now, this one has a lot going on. I have sine of x plus y, that's a chain rule. And then on this side, I have a product. So I'm going to encourage you to, again, just give it a try. Pause the video, try it. Use pencil so that you can erase if you need to. Let's see what you can make of it. All right, let's see what we got. So if I start with my derivative of sine of x plus y, the outside is sine, so the derivative of sine is cosine. Keep the inside the same. Then I'm going to multiply by the derivative of x plus y, which will be 1 plus derivative of y will be dy dx. Then on the other side, I'm going to use my product rule. So I have y squared times the derivative of cosine plus cosine times the derivative of y squared. Now I notice that in order to isolate my dy dx, I have to get it out of this factor. So this cosine of x plus y is needing to be multiplied by both of the terms here. So I distributed my cosine of x plus y in the next term, step. That's pretty much all I did. Then in the third step, I'm pulling the dy dx terms to the same side. So this cosine is still here, and I'm moving this one over, factoring out the dy dx at the same time, and then leaving this non-dy dx term and subtracting this one over. And so all that's left to do is divide by this multiplier of the dy dx to get my final answer.